There are many original ways to extract energy from the environment, from the sun, wind, tides, thermal energy of the earth, and then transform it into electricity. But the problem is the accumulation and storage of energy.
Capacitors, the electrostatic battery. Capacitors store the energy in an electrostatic field rather than in chemical form. They consist of two electrodes, plates of opposite polarity separated by a dielectric or electrolyte. The capacitor is charged by applying a voltage across the terminals, which causes positive and negative charge to migrate to the surface of the electrode of opposite polarity. Heat, the thermal battery. There are two basic types of direct conversation thermal batteries: thermocouple batteries. The system is not energy efficient and is only suitable for low power applications. AMTEC batteries, alkali metal thermal electric converter. They use a high temperature metallic the power working fluid. A solid electrolyte separates the electron flow from the ion flow, which gives up its energy to the electrons passing through an external load. Energy conservation efficiency is about 4 times better than thermocouple batteries, which makes them more suitable RTG batteries. Molten salt, a thermal battery. The molten salt battery is designed to capture the thermal energy from thermal solar arrays and release it overnight when the sun is not shining to generate steam for driving a conventional steam generator, and so maintain the energy supply to consumers. But today it doesn't get high applying. Ice battery, a thermal battery. The ice battery is a load-shifting thermal energy storage application specifically designed for air conditioning system, which stores cooling energy at night and delivers that energy the following day. It is a modification of a standard air conditioning system to extend its use to allow an alternative usage pattern to take advantage of lower off-peak electricity traffic during the night. Compressed air pneumatic battery. Compressed air energy storage (CAES) uses pressurized air as the energy storage medium. An electric motor driving compressor is used to pressurize the storage reservoir using off-peak energy. During peak times, air is released from the reservoir and mixed with natural gas to drive a gas turbine generator to produce electrical energy.
Pump storage, the hydraulic battery. Pump storage hydraulic electricity is another relatively simple method of storing and producing large amounts of electricity to supply high peak demands. At times of low electric demands, excess electrical capacity is used to pump water into elevated reservoir. When there is high demand, water is released back into the lower reservoir through the turbine generated electricity. The round-trip efficiency loss is around 20 to 30%, so that only about 70 to 80% of the electrical energy used to pump the water into the elevated reservoir can be regarded in this process. Superconducting magnetic energy storage, in other words, SMES, the magnetic battery. Superconducting magnetic energy storage systems store energy in the field created by a direct current flowing in a large magnetic coil, cryogenically cooled to a temperature below its superconducting critical temperature when an electrical currents flow without resistance or loss of energy. Radioisotope thermoelectric generators, RTG, the nuclear battery. Radioisotope thermoelectric generators, RTGs, were designed for the space applications and for providing power to remote installations such as lighthouses. These primary batteries are essentially nuclear-powered heat generators, which is used energy emitted by the natural decay of radioactive isotopes of plutonium to provide the heat which turn is used to generate electric power in a thermoelectric generator made from an array of thermocouples. Now, hydrogen storage. Electrolysis with fuel cells. Electricity can be converted into hydrogen by electrolysis of water. The hydrogen can be then stored and eventually re-electrified in fuel cells. The round-trip efficiency today is as low as 30 to 40%. Despite this low efficiency, the interest in hydrogen energy storage is growing due to its high storage capacity. Electrolysis. Water can be split into its component parts, hydrogen and oxygen, using proton exchange membrane technology, PEM. When a DC voltage is applied to the electrolysis, water molecules are oxidized at the anode, releasing oxygen, and electrons leaving protons, H plus hydrogen ions, in the remaining water. The protons pass through the PEM to the cathode, where they meet electrons from the external circuit, reducing the protons to hydrogen gas, which is released at the cathode. Hydrogen storage. Small amounts of hydrogen, up to a few ml, can be stored in pressurized vessels at 100-300 bar or liquefied at 20.3 kelvins. Alternatively, solid metal hydrides or nanotubes can store hydrogen with a very high density. Very large amounts of hydrogen can be stored in a man-made underground sealed caverns of up to 500,000 cubic at 20 bar, corresponding to a storage capacity of 167 GeV hydrogen, 100 GeV electricity. Hydrogen re-electrification. Hydrogen can be re-electrified in fuel cells with efficiencies up to 60%, or alternatively burned in combined cycle gas power plant. Storage capacity and power handling. The region plot shows the energy storage and power handling capacity of some alternative storage techniques. Thank you for watching us. Don't forget to subscribe.